I
Yes,
think
I
that
started.
I think you're muted.
It's recording now.
Can you hear me now?
Daniel, I think you're muted.
Can you hear me now?
Yeah.
Okay,
Yeah.
cool.
Yeah.
Okay.
Yay. Okay, so welcome everybody. And today we are very happy to have Daniel Brennan telling us about generalized families of TKTs.
All right, great. Thank you very much for the invitation. It's always fun to give talks like this. It's always fun to reach a bunch of different people. So today I'm going to tell you about a paper that I put out a couple months ago with Ken and Trilligator. And the idea is about generalizing what we mean by a family of quantum field theories. So I sort of want to break this down, this talk down sort of piece by piece. So first I want to talk about uh, what I mean by generalized. And by generalized, I mean this is going to refer to sort of the paradigm of generalized symmetry. So I'm going to start with a sort of brief overview of that, even though I think probably many people here are familiar. And then I want to talk about what families of quantum field theories are. And then finally, I want to do 1 plus 2 equals 3 and talk about how these two fit together to form some sort of new paradigm of what a sort of generalized family of quantum field theory might be. Right. So as I think many of you know, recently there's been a sort of paradigm shift in the way that we think about symmetries in quantum field theory. So the sort of new paradigm of, say, generalized symmetries, or sometimes called categorical symmetries, is that for every topological operator in a quantum field theory, you have an associated global symmetry. First, I want to say two things. First is that I want to apologize because I like to give chalk talks. And so this is the sort of closest thing I could think of about how to give a chalk talk over Zoom. And the second is that now I wanted to flag that sort of my approach or the way I'm going to talk about generalized symmetries in this talk is mostly going to be through sort of a more field theoretic approach. So I'm not going to talk about really lattice theories, although most of the things I think we talk about here can be applied to lattice theories. And I'm also going to stay kind of away from category theory. So this is going to be sort of a more classic old school uh, field theoretic discussion. Right. So as we know, sort of one of the simplest examples of a global symmetry is a group-like symmetry. And by this, I mean you have some set of topological operators, U sub G, where G it belongs to some group, and their fusion obeys the group law. Okay? So as we know, sort of one of these sort of group-like symmetries are generally called now higher form symmetries. Although sometimes we also refer to group-like symmetries and also including higher group symmetries, but I'm pretty much not going to talk about in this talk. But a higher form symmetry, we say, is labeled by some group G and some degree P. So here P is called the degree, where P is some non-negative integer. And this P form symmetry acts on P-dimensional operators. So the example that I'm going to talk about the most in this talk is what are called one-form symmetries in this paradigm. And those are the ones that act on line operators. So yeah, so we know that the way that these symmetry operators act on line operators is you take a line operator, and then the symmetry operators, I'm going to draw like this. This is my line operator. This is my symmetry operator u sub g. So this can link the line operator if it is on, because it's going to be a d minus 2 dimensional manifold, and it acts on the operator by, when you contract the UG operator passed to the line, you find that you get a phase when it passes it, and that enacts the group action. Okay, so hopefully this is things that people are already very familiar with. So in this talk, we're going to actually be using more of, as I said, a field theoretic approach. So, to a P-form global symmetry, in general, what you can do is you can couple your quantum field theory to a P+1 differential form. So this is really a P+1 value, a degree P+1 gauge field. So, and in general, to one of these UG operators, it turns on the P+1, which is some proportionality constant times the Pontryagin dual is the world volume. Like this. Oops. So here the idea is G is I'm using the example where G is a U1 P forms in the field, and this group element G is e to the I alpha. So this is sort of map. And the sort of nice utility of this is that once we have gauge fields, so with these sort of background gauge fields, you can do a lot more probing of the dynamics of your theory. So for example, we're going to be here focused a lot on anomalies. So in this formulation, you can think about the partition function as being dependent on your background gauge field. So let me write B here to be consistent. And you say that the theory, this symmetry is anomalous, or it has an 't Hooft anomaly, if the partition function is not invariant under background gauge transformations, but rather is only invariant up to some phase, which depends only on background gauge fields. So yeah, so this is sort of the way we can think about anomalies and how using this field theoretic formulation allows us to think about that. So good. So this is sort of the most basic version of a generalized symmetry that you can have. Sort of one of the first ones we talked about. But in this talk, we want to talk about more general ones. So I do want to talk about a particular type of categorical symmetry. But for this talk, I'm really just going to focus on the sort of subset, which are what I call non-invertible chiral symmetries. Okay, so sort of the most basic example of the non-invertible chiral symmetry happens in 4-dimensional U1 QED, which is massless. So in this theory, we know that if you take a Dirac fermion, there's a classical chiral symmetry where this rotates like this, where gamma 5 is the gamma 5 matrix. And so this symmetry, which I'm going to call U1 sub 5, is anomalous because of the triangle diagram. So here we have this J5, so the current associated to the symmetry has a non-zero 3-point function with gauge current, with two values of gauge current. And so what that means is that the conservation equation for the chiral symmetry is no longer true, but rather it equals this F gauge, wedge F gauge component. So now you have some sort of, the divergence is no longer 0, but it's equal to some non-trivial dynamical field. And what this tells us is that the symmetry operator you might have tried to construct, EDI alpha times the integral of star J5, is not topological. But we now know that there is a way to make it topological. And that is by adding a TQ of T on sigma, on the world volume of this operator. So in particular, we talk about this, the associated topological operator, which I'm going to write in this way. So here Q is a rational number. Sigma is a codimension 1 manifold. So this is the associated topological operator you can make is just this U times e to the iq. Well, it's really this sort of broken, not non-topological part. So e to the 2 pi iq. And then we multiply it by some three-dimensional TQ of T that lives on this world volume sigma. So here Q is equal to P over N. And this TQ of T is what we call the fractional quantum Hall state. So sort of by messing with these sort of topological, by doing these sort of topological manipulations, what we see is that we can actually sort of fix what appear to be broken global symmetries by doing these topological manipulations. But the price we pay is now that this is not a group-like symmetry. So these DQs do not obey sort of group identity. So if you fuse it with this operator with its sort of Hermitian conjugate, you don't get the trivial operator, but rather you get some decoupled TQ of T. Okay. So right. So one way to think about this, these operators, rather than you can think about them as saying I have some surface which splits my spacetime in half. So instead of thinking about putting some fractional quantum Hall state here, instead what you can think of is saying I have my symmetry, I have my theory on one side, it has an action, which is, I guess, dependent on my fields, A, the gauge field, and psi. And then on this right-hand side, on the other side of my symmetry operator, this is T sub Q, I actually am doing some discrete gauging. So I take the theory and I gauge a Zn subgroup of the one-form global symmetry. This is the magnetic one-form global symmetry. And now my action has some new dynamical fields in it. It looks something like this. So you have some new auxiliary dynamical gauge fields, A1 and B2. B2 wedge. And then you have a torsion term. Okay. And so you can trivially integrate out these fields, or not trivially, you can integrate out these fields, A1 and B2. And what you find is that when you integrate these fields out, they only have edge modes on the boundary, which are exactly this quantum Hall state. But it is sort of a nice way to think about it because you can say this operator, this surface operator is really relating the theory to a gauged version of the theory, which happens to be identical to it. Right. So this is some really nice manipulation, but there is something really cool that we can say about the quantum field theory that from this symmetry that's genuinely new. And it's that, so if we essentially what we can say new things about when the symmetry is emergent. So if we imagine some sort of RG flow from a UV theory down to our IR theory, and this is just our massless QED. And we say that the UV theory has no global symmetries, or at least it doesn't have the U1 one-form magnetic symmetry or the sort of non-invertible chiral symmetry. So if the UV theory doesn't have either of these symmetries, maybe I'll just write it like that, then what we know is that in the infrared, these symmetries are emergent. But the structure of these global symmetries, since they have sort of nested categorical structure, much like the way that groups can have nested subgroups. And what that tells us is that they have to emerge in a way that respects that nested structure. So the sort of one-form symmetry must emerge first, essentially, before this non-invertible symmetry. Let's write NIS down here. And that's because you needed to gauge the one-form symmetry in order to even construct the non-invertible symmetry. And so this is something that's sort of genuinely new about these non-invertible symmetries. Okay, cool. So very good. So before I jump onto the next topic of categorical families, I wanted to sort of just briefly mention a couple things about the symmetry TFT because it's sort of going to be instrumental in the way that we're going to think about these generalized families of theories. Okay, we'll just go to the page. Right. Right. So symmetry TFT is something that's really cool. And I believe that the terminology was coined by someone here in the audience. But yeah, so the idea of the symmetry TFT is that it's sort of an extension, sort of like an extension of the idea of anomaly inflow. In the sense that what you sort of think about your d-dimensional quantum field theory as sort of being at the boundary of some d+1 dimensional higher theory. So in the idea of anomaly inflow, what you have is some sort of trivial theory that your quantum field theory lives on its boundary. And in that story, the trivial bulk theory is just sort of encoding the anomaly. But in the idea of the symmetry TFT, you actually have a sort of non-trivial TQFT in d+1 dimensions. And this is going to just not just encode the anomalies, but rather the entire symmetry structure of the quantum field theory. So, right. Let me fix this picture. So we have our quantum field theory here. We have some sort of topological boundary here, which is sometimes we call the quiche. And so for every symmetry operator on the boundary, you can list it to a symmetry operator here in the bulk. And to every charged operator on the boundary, it lives at the end of another topological operator that stretches between the two boundaries. And the way that the symmetry operators act on it is enforced by the linking of the operators in the bulk. Okay, so this is a very powerful mechanism to study the symmetries in the quantum field theory. And there's sort of a crucial role played by this quiche boundary condition, in the sense that since this bulk is topological, you can actually sort of imagine collapsing this interval, and sort of then you can think about the quiche boundary as, in a sense, acting on the quantum field theory. So what it really does is this sort of restricts or determines how symmetry acts on your quantum field theory. Right. So so usually what we do is we take this quiche boundary condition and we think about it as a state in the Hilbert space of my SimTFT. And then to get the partition function, what you do is you take this thing that we're going to just call the quantum field theory state, which is also in the Hilbert space of my symmetry TFT, and the inner product here of these two states defines the partition function of the quantum field theory with the particular symmetry structure defined by the quiche boundary condition B. So maybe, yeah. So sort of foreshadowing what we're going to talk about in just a bit, you can sort of think about it as saying this QFT state really is sort of really not just a single quantum field theory, but really encodes an entire family of quantum field theories in the sense that you sort of, this state tells you everything about your quantum field theory, and then project onto a particular representative, which is the way that the symmetry acts. So this is sort of where we're going. Family projection. Okay. Very good. So maybe given the audience, I will skip the example of how Zn symmetry shows up as described by the symmetry DFT, unless there are any objections. Okay, cool. So good. So now I want to talk about what sort of families of quantum field theories, sort of what this means and what you can do with it and why it's great or not great. So good. So everything I've told you so far is about what you can do in quantum field theories with symmetries. But now the question you might want to ask is sort of, what can you do, or rather, what can you learn about quantum field theories from explicitly broken symmetries? So for example, by explicitly broken symmetries, what I really mean is you can add symmetry breaking interactions in a Lagrangian theory. So where we're going with this is that sort of first we're going to look at the case for ordinary that is zero form global symmetries. And so in this case, we're imagining that you have some operator O of X that transforms under your zero form global symmetry in some non-trivial representation. And then what you want to do is take your action and you're just going to add some interaction which looks like lambda times the integral O of X d over dx. So here lambda is just some sort of, in general, some complex or real valued parameter. So maybe we'll take this to be complex and a plus complex conjugate here. And this interaction breaks the symmetry. However, something you can do is you can pretend for the moment. Okay, so I'm gonna write this. So what you can do now is pretend that lambda is the expectation value of some scalar field. So pretend lambda is the expectation value of some scalar field. And then this is some sort of spontaneously broken global symmetry. But you can think about it this way, or you can think about it as just saying, well, I'm just going to assign some G transformation property to lambda such that lambda O is G invariant. So then what you find is that your quantum field theory, T, will generally be labeled by this coupling constant lambda. And this G symmetry now relates T of lambda to T of, well, say just G dot lambda. So what that is, since this is a symmetry of the theory, is an equivalence between the theory at one point and the G orbit. And so what this means is now you can actually think about comparing the partition function and all the dynamics of the theory at these different coupling constants. So, right. So maybe I'll give you a nice example that we can sort of, I can tell you some more of the structure. So my favorite example based on when I grew up is four-dimensional SUN Yang-Mills plus a single adjoint fermion. This is also known as 4D SUN n equals 1 superannuals. Right. So this theory, okay, maybe I will take this on the next page. That might be better. Right. Good. So this theory is nice. It has some global symmetries. It has a Zn one-form global symmetry, which is the center symmetry. It has a U1 zero-form R symmetry, which is broken and spontaneously to a Z2n zero-form global symmetry by an ABJ anomaly. And these two have a mixed anomaly. Right, so the anomaly you can write down as a phi dfbt. It just looks like 2 pi I over n, a1 to p of b2 over 2. So here, a1 is the Z2n zero-form symmetry field, and b2 is the Z and one-form symmetry field. Okay, good. So because of this mixed anomaly, we know that the infrared cannot be trivially gapped. And in fact, this theory is, I'll say, relatively solvable. We know that it flows to a gapped theory in the infrared, where the Hilbert space just looks like a direct sum of trivially gapped vacua, and there's n equals 1 through n of them. And at each one of these vacua, call this omega sub n, there is a SPT, which just looks like 2 pi I n over n p b2 over 2. That's literally just because the, essentially it's the different expectation values you have from spontaneously breaking the Z2n R. So this infrared theory is the spontaneous breaking of Z2n goes to Z2. And that's what leads to these different SPT phases. Okay, so here's a nice control theory that we can talk about its family related to it. So think about a family. Sorry.
We can't see your iPad.
Yeah, sorry, I accidentally hit the off button. Okay, right. Right. So what I want to do now is I want to look at a family of theories where I add a mass term. So m psi plus complex conjugate. So here m is some complex value parameter, and so this term will in general break Z, essentially the discrete R symmetry completely. And what I want to do now is I want to actually just restrict m along a circle in the space of masses. And that's just because we want to sort of take an exactly marginal deformation, or I sort of only want to look at an exactly marginal family of deformations, because if you start messing with dimensional parameters, they'll run in the infrared, and then it's a little bit, I don't think you can really think about the family as nicely. But anyways, so what this does is it gives us some family of quantum field theories that's labeled by this phase theta. And so now what we want to do is we want to talk about what happens if you treat theta as a spurion. So if you transform psi goes to e to the e to the 2 pi I over n times psi, then we want to shift theta goes to theta minus 2 pi over n. Okay, and so when you do this, then you sort of artificially restore the Z2n, well, the discrete R symmetry, and you get a relation between the theory with some generic value theta, and the theory where theta is shifted by 2 pi over n. Great. So now you have a nice family of theories, but what's great about this is now you can also talk about an anomaly for this family. So I like to call these family anomalies, although they go by many words now. And so what happens is that when you look at the partition function at a given value of theta with the one-form symmetry turned on, you find that it's not going to be invariant under shifts by 2 pi over n, but rather you're going to get Susan phase, which is just 2 pi I over n times the integral of Pontryagin square b2 over 2. So this is sort of an anomalous phase. There's no gauge invariant counter term you can add to get rid of this phase. And what you can actually show is that if you think about some RG flow, some family of theories. So we imagine the UV theory, which is dependent on theta. And then we look at the family of IR phases. They're also going to depend on theta. What this anomaly tells you is that you have this sort of decision tree. So if you were to flow to a gapless theory, all would be well. All anomalies can be mapped in gapless theories, I think. Anyways, and if you flow to a gap theory, then essentially there are only two options. You can either have spontaneous symmetry breaking, or you must have some phase transition in theta. And so it turns out for this theory, what happens is that you actually get a phase transition in theta. And the reason is that at theta is equal to pi over n, there's an emergent T symmetry, time reversal symmetry, that has a mixed anomaly with the Z and one form global symmetry. And together, these tell you that there's a Z2 level crossing at that point. Very good. So, but more generally, you can think about what happens more broadly in quantum field theories. So if you can sort of phrase everything I just said about this partition function as saying, well, essentially what's happening when you have one of these anomalies is I have my partition function, and it depends on this parameter, which I'm still going to call theta, and it depends on all these background gauge fields, which I'm just going to generally call B. So,
Sorry, just to be sure, because
yeah.
before you said phase transition, but below you said level crossing. So I think this is real level crossing, phase transition.
Yeah, very good. That's a good call. Good. So, more precisely, what I mean is not really phase transition, but is that you cannot have essentially the Hilbert space has to vary discontinuously.
Yeah. Okay, so you
So
change back, but you are in the same phase.
yeah, exactly. So the correct statement is that you can have a discontinuous Hilbert space function of theta. But yeah, the correct statement is that you can prove that you cannot have a continuous family of isomorphic Hilbert spaces over this orbit when you have this anomaly. Right. Good. But so essentially what's happening when you have one of these anomalies is you have a partition function and you think it's a function of this parameter theta and of the gauge fields. But what you find is that essentially it's not actually a function but rather it's a section of a line bundle. Oops. Over this parameter space, which I guess I'll just call C sub theta. And of all the space of background gauge, shall this be curly G. So. Okay. Right. And so you can also think about all of this discussion about saying, well, if you have this spurion analysis that allows you to compare the theory at different points, as saying that when you add the deformation, before you realize there's any symmetry, the partition function truly is just a function of this parameter. But then when you say, oh, I have this identification now of these theories, what you're actually doing is taking the quotient of the parameter space by identifying the theory at different points in this parameter space, which allows you to actually have non-trivial cycles along which you can have polynomies. And that's why you have anomalies in space of these families. Okay, good. So I think that's everything I wanted to say about those. So let's go on to generalized families. And so the question now we want to ask is sort of what is the structure of quantum field theories that arises when explicitly breaking sort of more general categorical symmetries. So I think actually I don't have the complete answer to this. But what I'm going to talk about is what was in our paper, which is at least a partial answer. And so essentially what we're looking at is the sort of, so we're just going to study the non-invertible chiral symmetries. But in principle, this sort of analysis can be generalized to any sort of categorical symmetry with an action on a local, gauge invariant local operator. So sort of following the pattern of naming, I want to call the family of theories that arise non-invertible families. So let's again just go back to this example that we just did. We said 40 SUN n equals 1 super Yang-Mills. So this theory has a ZN1 form symmetry. And what you can do is you can construct a theory that has a non-invertible symmetry out of it by gauging the one-form symmetry. So then you get a Z 40 PSUN n equals 1 super Yang-Mills. So again, this has a ZN one form magnetic symmetry. And now the Z, what we call the R symmetry, I've been calling the R symmetry the whole time, the Z2N zero form symmetry, I will write up here, upon gauging becomes, sorry, get the color, becomes a Z2N non-invertible symmetry. And essentially, this is exactly the same sort of chiral symmetry that we were talking about earlier. What happens is that the anomaly of the UV theory, I'm just going to write it here, I guess. Give me some space. Let's try it again. So we have this anomaly of the UV theory. And when you gauge the ZN one-form symmetry, this becomes an ABJ anomaly. Where now this W2 is summed over. This is BPSUN class. So now you have exactly what it looks like from before, where you have this sort of ABJ type anomaly that is breaking the group-like Z2N symmetry. And again, you can just sort of fix it by making a non-invertible symmetry by dressing it with a fractional quantum Hall state. Very good. So now you sort of run into this problem, though, of saying what is, well, okay, let me finish describing the theory. What we know is that in the UV, we have this PSUN theory, and then in the infrared, you get some non-trivial infrared structure, which is essentially what we've done now is we've just taken the same IR theory from before, and then we've just gauged the ZN one-form symmetry. And if you recall from over here, we just have n-degenerate vacua, which are each different SPT phases. But each SPT phase actually depends on the one-form background gauge field. So what you get in the infrared over here is you actually get a ZN gauge theory in the infrared. You get n copies of it, where you're twisted by this WN class from the other page. Okay, so again, this is what happens sort of when you have this Z2N. Now it's a non-invertible symmetry that is spontaneously broken to the Z2, which is still a group-like symmetry. So this is the structure that arises when you have this spontaneous symmetry breaking. Right, very good. So now again, we can sort of think about the family of theories here, and then look at what structure arises. So let's again add the mass term. So I guess they could keep calling the interaction term, but anyways, m psi psi plus complex conjugate. And so then this again explicitly breaks this now non-invertible global symmetry. Right. So let's see what this does. So now we want to add some sort of non-invertible spurion paradigm. And so to do that, I want to use this picture of the half-space gauging. So the idea now, recall, is that on one side, I have the theory, and it has this mass m. So again, I'm going to write m as some positive mass scale times the phase, and then I'm just going to say the theory depends on theta. So on one side of the relation, I'm going to have this theory T, which is depending on theta. And then if you were to do a broken non-invertible symmetry transformation, where you say M transforms by to preserve the symmetry, then on the other side you find T with theta plus 2 pi over n, and then you've gauged the Zn one-form global symmetry, which is part of the broken non-invertible symmetry. So here what I'm doing is essentially utilize the fact that if you look at these symmetry operators, when they act on the spurions, they really act as a domain wall between two equivalent theories. But now you see that we have a relation between a theory with some parameter value and a different parameter value, but the theory is also gauged. So the question is sort of how would you make sense of this as some sort of generalized family? And the way that we want to think about it is by using this picture that I was advocating for earlier in the symmetry TFT. So as I said, early in the symmetry TFT, we have this quantum field theory state, which we've been writing as a bra. And to get a partition function, we really write it as the inner product of this quantum field theory state with a particular quiche boundary condition. So now if we wanted to consider this quantum field theory, which depends on a parameter, we could. Theta. And then this would produce, what's it called? Be like this. This would produce the partition function with the given, say, background gauge field, for example, at a particular value of theta. But now we see that in this by using the structure of the symmetry TFT, this gauging is just a linear transformation on the Hilbert space of the symmetry TFT. So really, if you think about the family of quantum field theories as being labeled by the different type ways you can project out this quantum field theory state down to a partition function, then this is sort of gives you a more broad way of thinking about it. So in other words, what I'm saying is that you could think of a generalized family of quantum field theories as the sort of not orbit, but it's the sort of space of deformations, such as by local operators that you can insert into path integral, plus topological deformations or topological manipulations. And that's literally what I've sort of done up here in this picture. The idea is I have some theory and I want to construct some domain wall. But so there's multiple different types of domain walls you could construct. You can construct the one where theta just shifts by 2 pi over n, but then you would have two different theories on each side. That's fine, but that's a domain wall you can construct. But you could also construct this domain wall where you shift theta by 2 pi on both sides, and you do the topological manipulation, which is just a discrete gauging. So then you have the same theory on both sides, and you can make nice identifications. So what you might say then is when you have these sort of symmetries, so we'll just call these symmetry transformations S in general. Say you have some T of theta, which goes to T of theta prime, possibly acted on by some sort of topological manipulation, such as gauging. Then you might say that the partition function, for example, is not a line bundle over, not a function, but rather is a line bundle over the space of coupling constants times the Hilbert space of the symmetry TFT. And that these sort of symmetry transformations, S, allow you to quotient this space and reduce it. So then when you have these sort of identifications, you can again compare partition function along theories that look a priori different. But once you realize they're part of some sort of non-invertible symmetry, you can compare their partition function in Hilbert space, and you'll see that they're the same, except that you might have, in taking some path from going from one to the other, you might have activated some sort of anomaly. So that's actually the next thing I wanted to talk about real quickly. Is that, so first of all, this is some sort of nice, well, I think it's a nice structure, but I think that some question you should always ask is sort of like, why is this useful? What can I do with it? I don't know what you can do with it necessarily. I haven't been able to solve any problems, but in theory, there are a lot of cool things you get from this, right? So whenever you sort of break a symmetry, in general, you lose a lot of information. But if you use this to get use this paradigm of generalized families of theories.
But I'm a bit confused by something. The Hilbert space of SymTFT depends on the manifold where you evaluate the SymTFT. While here, I don't think this should depend on the manifold. So maybe it's not really the Hilbert space, it's more like the set of possible topological boundary conditions.
Yes, that is, well, good. I had thought about the set of topological boundary conditions as Hilbert space of the symmetry TFT by just using this open-closed duality. But I guess then it has manifold dependence, which is what I guess what you're complaining about.
Yeah. Yeah. Yeah.
Yeah.
Okay.
There is a more general version of this where you also take, I think in the paper by Clay and Dan Fried and friends, the anomalies in the space of coupling constants, they actually also put explicit manifold dependence down here.
Mm-hmm.
And I think that was, but I think that might have just been to get the um, gravitational like family anomalies as well. Yeah,
Okay. Okay. I think I understand. Okay.
yeah. Right. Okay. So I guess in the last 10 minutes, I'll tell you sort of what are the things this buys you. Um, so the first is that, well, is that it sort of preserves, or say, you know, it doesn't preserves not the right word, and sort of maps anomalies onto sort of generalized family anomalies. And again, you can sort of show that these families have the same sort of behavior. So if you have some, for example, if you have some UV theory. So okay, here's the setup. So you have some UV theory, and which is some sort of generalized family, and it has some sort of generalized anomaly. Then in the infrared, you again get some family of theories, and you get the sort of split decision tree again. You get the sort of possible gapless theories. And then if the theory is gapped, you can show that either there has to be spontaneous symmetry breaking, or there has to be a sort of discontinuous Hilbert space with data. So that's one thing. It's also quite, this structure is also nice because this is actually exemplified in this example, is what you actually find, you can actually understand this entire symmetry breaking of the PSUN super n equals 1 super Yang mills, and what happens when you explicitly break in terms of the sort of family anomaly that you would get from explicitly breaking the Z2n non-invertible symmetry. But what you can do is you can actually compare the SUN and the PSUN theories. So in the SUN theory, here you had this sort of anomaly, and what you don't have any sort of, or in the infrared you get some sort of family of anomalies. So yeah, let me draw a picture. This is nicer. Okay, so in the SUN theory, UV, in the infrared, you get the sort of family anomaly. So the SUN theory has the Z2n zero form symmetry, which is explicitly broken, and you get a family anomaly. Yeah, so in the infrared. So then if you gauge in the PSUN theory, you get a Z2n non-invertible symmetry. And then spread, you get a non-invertible family anomaly, which is sort of controlling everything. Or this is when you break M to M. But you can also sort of find, you get this entire commuting diagram. Again, so what essentially happens when you go from this family anomaly to this non-invertible family anomaly down here in the bottom is you can sort of break the symmetry, and then you can try to gauge the one-form symmetry. And then what you find is some sort of family with an ABJ anomaly, essentially. And what you realize is that if you take this sort of more general picture of what a family of quantum field theories is, you can take this family ABJ anomaly and just realize that actually you have some non-invertible family of theories. So this is the first thing that I wanted to point out. And the second one is that you sort of can preserve. Yeah, so you sort of get to preserve the UV completion story. slash emergent symmetry hierarchies. Right. So the picture was like this. So I have my UV theory without any global symmetries, we'll say. And then in the infrared, I have this emergent, say, non-invertible symmetry. So if I had, for example, some group-like symmetry, oh, my G's look too similar. Let's call this a C instead of a G. So if I had this sort of nested categorical structure, I would say that the group-like part has to emerge before the categorical part, for example, in these non-invertible chiral symmetries. But we can also look at what happens when you do some sort of symmetry breaking deformation in both the UV and the infrared. And so what you find is that, again, you get this nice commuting diagram. So now what happens when you sort of do this symmetry breaking deformation is you have some sort of family of theories. But what happens is in the infrared, you actually get some enhanced family of theories. So instead of having this categorical symmetry structure, you have this sort of categorical family structure. And what you find is that, again, because of you're not really changing the physics too much in these examples because everything is controlled by this Spurion analysis. And so what you find is, again, that the symmetry, this sort of normal symmetry group that feeds into the non-invertible symmetry has to emerge before this sort of generalized family structure emerges. So there's this sort of nice parallel structure that happens. So EG is bigger than the categorical symmetry, emerges before the categorical symmetry, sort of tells you that in the broken story, the symmetry still has to emerge before the categorical family structure emerges. And I think I'm just about out of time. But I wanted to say that a couple things. One was that yeah, so this has a really nice structure that's actually very nice for higher group symmetries. So for higher group symmetries, you can just imagine that you're only breaking the zero form part, and then all of the one form symmetry parts are just preserved. So the G0 inside of some CN group is broken. And then what's happening is that when you sort of move along your family of theories, so if you go through a G0 broken orbit, then the sort of way that you preserve this full higher group family or higher family is that you would sort of also shift the higher gauge, the gauge fields, the background gauge fields when you shift this background parameter. And that fits very nicely into this picture of the symmetry, the Hilbert space of the symmetry TFT. You would say that maybe my coupling constant space times the space of all my background gauge fields for my higher group gets this quotient structure where shifting, translating in this space leads to a translation in this space. This fits nicely inside of this coupling constant times the symmetry TFT of the Hilbert space mod lambda. And the other thing I want to advertise is that in our paper, we do some nice computations, which I don't have time to show you. But this example of the 40 n equals 1 super Yang-Mills has a really nice match because you can actually, for example, say a lot of nice things about if you take 40 SUN super Yang-Mills and you add higher order coupling or high dimension operators, like some psi to the n. And you can also sort of study how this all behaves under discrete gauging and going to 40 PSUN super Yang-Mills with the sort of same interaction. And in these two cases, you're going to be breaking different amounts of the Zn of the R symmetry. So here you have the Z2n zero form symmetry again, and here you have the Z2n non-invertible symmetry. and they're both going to be broken by different amounts by this sort of higher dimensional coupling constant. And you can have very good control over both cases by using this structure. So I think I'm out of time, so I'll stop there. And thank you very much.
Thanks a lot for this very nice talk. So questions? Maybe I can start with one. So at the beginning, when you were talking about just the families of PFTs, not the generalized ones. So I guess that in your example, in fact, the theories that were related by the theories in the same family must be in the same phase, right? While in the generalized case, I feel like they must be in different phases. Is that correct?
I don't think so.
What I have in mind is simply that when you do this sort of like Spurion analysis, you're trading explicit breaking for spontaneous breaking, and when you spontaneously break an ordinary symmetry, two theories that are related by the symmetry are in the same phase. While for non-invertible symmetries, they must be in different phases somehow.
Oh, sorry. I understand what you're saying. Yeah, so good. So, right. So this is a nice example. So, right. So spontaneously broken phase, everything is uniquely gapped, or like each of the vacua is unique vacuum. It's just given by the expectation value of some the order parameter is this I guess people call lambda lambda, but I think in my notation it was this operator. This determines which phase you're in. Right. So when you do the gauging, okay, sorry. When you add the mass term, what you're doing is you're actually picking out, I think, just one of these vacua. And then what's happening is you imagine, okay, see if I can fit this in here. So you imagine some plane where the expectation value can take. And there are just n points around the circle. And if things are nice, what you're doing is essentially picking a ray in this plane, or not a ray, but actually a line. And what's happening is you're sort of in one vacua for each segment, and sort of where you cross a line or cross a point, then there's a degenerate vacua. Right. So in this example, but when you do the gauging, it's the same sort of inference structure, except each of these vacua actually looks different because of this this twist. This torsion term actually will trivialize the gauge field generally. So I think the answer to your question is then probably yes.
Yeah, I agree. Okay, thank you. Other questions? Since we don't have further questions. Okay, so in that case, thanks again, and let me stop the recording.